Hello, Mr. Betts here. Let's take a look at an example using the alternating series error bound. So we have a series here that is going to converge by the alternating series test. So you can notice here as k gets bigger, the terms are getting closer to zero and the terms are alternating. So this series is going to decrease in magnitude to zero. At least the terms in the series are, which means that the series itself converges by the alternating series test. So if we look at the nth partial sum given by this expression right here, essentially just plugging n in up here instead of infinity, we want to know if we look at any particular partial sum, what is the least value for n? So which partial sum is going to give us an error less than 1/10,000th? So remember this expression right here means the error. So S is the infinite sum, S sub n is the partial sum. And we want that error, we want our partial sum to be off by less than 1/10,000th. Well, if you remember this error bound right here, the error is bounded by the magnitude of the n plus first term. So essentially what we want to do is we want to figure out what is the value that we can plug in for n that's going to make that n plus first term smaller than 1 over 10,000, or at minimum equal to 1 over 10,000. So the n plus first term is going to be, and remember we're doing absolute value, so I'm just going to put a 1 on top here. So it's going to be 1 over 2 to the n plus 1. So that's going to give us the n plus first term, and we want that to be less than or equal to 1 over 10,000. So essentially what we're going to do here is kind of a trial and error. So we want to figure out, okay, what does n need to be to make this less than 1 over 10,000? So if we wanted to evaluate this numerically, we can do some cross multiplying here. And I'm going to go ahead and work this out. 2 to the n plus 1. Then we can take the natural log of both sides. So when we do that, that's not going to change the order of my inequality. Just like multiplying by 2 to the n plus 1 times 10,000 is not going to change the order of my inequality. And this is going to give us n plus 1 times the natural log of 2. This is why I used a log to begin with, so that I could take that exponent out front. So then we have n plus 1 is greater than or equal to the natural log of 10,000 over the natural log of 2. And then if we subtract the 1 from both sides, we know n has to be greater than the natural log of 10,000 over the natural log of 2 minus 1. And that expression, if you just plug it into your calculator, is about 14.3 something. Okay, all that really matters is n has to be greater than or equal to that, but also keep in mind that n has to be an integer. So the least value for n is going to be the next one, which is going to be 15. So this is going to be n equals 15, and that term then is going to guarantee that our error is going to be less than 1/10,000th. I will say that this numeric approach is not really necessary. If we have a calculator accessible to us, it might be quicker to just do some trial and error. So plug in various numbers for n into this expression, and just try values until we get something that gives us something less than 1 over 10,000th. So trial and error is perfectly acceptable here, and that's going to give us the same answer.